Hi, my name is Aditya Patankar and I'm part of the Interacting Robotic Systems Laboratory at Stony Brook University, New York. Today, I will be talking about hand-object contact force synthesis for manipulating objects by exploiting the environment. Capabilities of a robotic arm hand system like dexterity or payload capacity can be enhanced by exploiting contacts with the environment. The figure on the left shows how dexterity can be improved. The contacts with the environment can be used to reposition or reorient an object which is already grasped. This has been coined as extrinsic dexterity and studied in the reference 1. The figure on the right shows how payload capacity can be improved. We can reorient a heavy object by using the environment as a support to balance part of the weight of the object. Our overall research goal is to formalize the problem of enhancing payload capability of a manipulator and develop planning control algorithms for it. In this paper, we'll focus on the planning part. Note that, intuitively speaking, for any manipulator, an object is considered heavy if the joint motor torques are not enough to balance the weight of the object. A common strategy used by humans to manipulate heavy objects is to lift the object by pivoting it on one edge while maintaining continuous contact with the environment. This is essentially done so that our arms do not bear the full weight of the object. When we do this, the reaction forces at the object-environment contact can be used to partly balance the weight of the object. This in turn reduces the contact force required to grasp the object against the effect of its own weight. So, our goal in this paper is to formalize the problem of computing the grasping force at the hand-object contact so that the robot can utilize the environment to manipulate heavy objects. We call this the grasping force synthesis problem, which we will discuss in more detail in the next slide. As stated before, the overall objective is to exploit the object-environment contact in order to manipulate heavy objects while maintaining continuous contact with the environment. To do this, we need to solve a key subproblem which involves developing a method which would essentially allow us to compute the contact forces at the object manipulator contacts while satisfying the following constraints. First, we need to satisfy the contact constraints to prevent undesirable slippage at both the object manipulator contact and the object environment contact. Second, we need to consider the equilibrium constraints which ensures force balance so that the object is not lost from the grasp during manipulation. We also need to consider the manipulator joint torque constraints, which ensures that the joint actuators would be able to generate the necessary forces at the hand-object contact. Our key contribution is that we have solved the grasping force synthesis problem for increasing the payload capacity of a robotic manipulator by formulating the problem as a second-order cone program, or SOCP. Since the SOCP is a convex optimization problem, it can be solved efficiently with existing optimization methods like interior point methods. In our paper, we have demonstrated the SOCP-based force synthesis method by simulations on single-handed and dual-handed robotic platforms. Recall that a second-order cone program is a special class of convex optimization problems, and they are defined as follows. We have a linear objective function subjected to a second-order cone constraint. Here x is the optimization variable and a and f are the matrices of appropriate dimensions. As we will show later, our optimization formulation for the grasp synthesis problem will have the mathematical structure of a SOCP. There is a significant amount of literature on computing grasping forces for stable force-closed multi-finger grasps. Different formulations including linear programming, linear matrix inequality, and second-order cone programming have been used for these problems. Linear programming formulations assume that the friction cone is approximated as a polyhedron. Linear matrix inequalities and SOCPs both use quadratic friction cone models. However, SOCPs give the most efficient solution algorithms. The problem of computing optimal contact forces was first formulated as a SOCP by Lobo et al. A fast interior point algorithm for the same, considering the point contact friction model, was developed by Boyd. However, in these papers, all the contacts were with actuated fingers. That is, the contact forces could be directly controlled. In this paper, we consider the object-environment contact also, where there is no direct control of the interaction forces. This is our general optimization problem formulation for computing the optimal contact forces for manipulating an object while maintaining contact with the environment. The objective function is subjected to the following constraints: the equilibrium constraints, the manipulator joint torque constraints, followed by the contact constraints. I will explain all these constraints one by one in the upcoming slides. First, we have the contact constraints. The contact constraints are the constraints imposed by the contact model on the forces that arise at the contact locations. In general, we have two contact models: point contact with friction model and soft finger contact with elliptic approximation. In our paper, we have assumed that the contacts between the object and the environment are point contacts with friction, and the contacts between the object and the manipulator are soft finger contacts. Note that both the friction cones for the point contact with friction model and the soft finger contact model are second order cone constraints. To guarantee that the object is not damaged by the contact forces at the contacts between the object and the manipulator tips, we can consider an upper bound constraint on the normal contact forces. Here Fn max is the upper limit for the normal contact forces. And both the second order cone constraints for the friction models can be expressed compactly as shown here. In this paper, we have assumed that the manipulation is quasi-static and therefore the inertia effects and dynamic forces are very small and can be ignored. The equilibrium condition is evaluated with respect to the object reference frame and can be returned as follows. Here, GC is the manipulator contact matrix, which is also known as the Grass matrix, and GE is the environment contact matrix. In the same equation, FC is a 6x(n) matrix containing all the object manipulator contact wrenches. Similarly, FE is a 6x(m) matrix containing all the object environment contact wrenches. The equilibrium constraints are a set of linear equations. While performing any manipulation or grasping task with the help of robotic manipulators, we need to compute the joint torques which generate the necessary wrenches at the object manipulator contacts. The relationship between the joint torques and the contact wrenches is given by the first equation. Here, Ji is the Jacobian matrix of the ith manipulator or the finger, and tau g is the torque for balancing the gravitational forces acting on the manipulator. The above equation can be expressed more compactly as follows. To ensure that the joint actuators are able to generate the required joint torques, we need to specify the joint torque constraints as given here. In this equation, tau min and tau max are the lower and upper limits of joint torques respectively. These constraints are also a set of linear constraints. When all the previously described constraints are satisfied simultaneously, the object can be stably grasped and manipulated quasi-statically with the help of the environment. Therefore, we have defined a general optimization problem for the same. The friction constraints are second-order cone constraints, and all the other constraints are linear. Therefore, if the objective function is linear, our grasping force synthesis problem can be modeled as a SOCP. Based on the choice of the objective function, we can further define different variations. If we seek a contact wrench that minimizes the contact forces, then we have a grasping force optimization problem, or GFOP. There are many possible choices of the objective function here. Two possible choices are as follows. First, we have an objective function which minimizes the maximum hand-object contact forces exerted by the manipulator along the normal component. Intuitively, this objective allows us to manipulate the object while minimizing the squeezing force on the object. Second, we have an objective function which minimizes the Euclidean norm of the vector of all the normal hand-object contact forces. Similarly, if we seek to minimize the manipulator joint torques, we have a torque optimization formulation, or TOP. Here also, there are many possible objective functions. We can have an objective function which seeks to minimize the value of the maximum joint torque, or an objective function which minimizes the Euclidean norm of the vector of joint torques. We have applied a grasping force synthesis formulation described in the previous slides for two different manipulation scenarios. In both examples, we want to reconfigure an object from a horizontal position on the support surface to a vertical position. Also, in both cases, the joint motor torque limits do not allow the manipulator to use the pick and place strategy because the porters are not powerful enough to balance the whole weight of the object. In the first example, we consider manipulating a hollow cylinder from the horizontal position to a vertical position, as seen here with the help of a parallel jaw gripper. We consider two cylinder gripper contact frames and one cylinder environment contact frame. We have used the GFOP formulation with the objective function used to minimize the maximum magnitude of the normal contact force at the cylinder gripper contact. There is also a restriction on the maximum grip force which can be exerted by the parallel jaw gripper at the contact point in the normal direction. The simulation parameters have been described in this table at the bottom. In figure 7, the graph on the left shows the variation of the cylinder gripper contact force in the normal direction on the x-axis with respect to the cylinder tilting angle alpha on the x-axis. And the graph on the right shows the variation of the cylinder environment contact force in the normal direction on the y-axis with respect to the tilting angle alpha on the x-axis. As seen from the graph on the left, initially the magnitude of the contact forces acting in the normal direction for one of the contact locations is greater than the other. This is because the normal contact forces of one contact opposes the gravity, whereas the normal contact force on the other contact acts in the same direction as gravity. Also note that the normal contact forces at both the contacts decreases as the angle alpha approaches approximately 55 degrees. At this point, the center of gravity of the cylinder is above the support point, so majority of the weight is supported by the ground environment contact. The magnitude of the environmental contact force varies accordingly to maintain the force balance. The maximum contact force in the normal direction which is required for this task is approximately 25 Newton. If we wish to implement the pick and place strategy, we need to remove the environmental constraints from our formulation. The resulting formulation is infeasible because we have an upper bound constraint which does not allow us to exert a force greater than 30 Newton. Therefore, our results reflect the fact that while manipulating a heavy object, we can overcome the constraints imposed by the manipulator capabilities by making use of the environmental contact. For our second example, we consider a heavy box to be reconfigured by the two-arm Baxter robot. We consider two box end effector contact reference frames and two box environment contact reference frames, as shown in the figure. Each arm has 7 degrees of freedom. In this example, we have also considered the actuator limits at each joint. Along with the JFOP formulation, we also use the TOP formulation to minimize the magnitude of the maximum joint torque in a particular joint of the Baxter arms. In figure 8, we have the graphs which show the variation of the box end effector contact force and the box environment contact force, both along the normal direction with respect to the tilting angle alpha on the x-axis. From the graphs, it is evident that the value of alpha increases, the magnitude of the contact force decreases at the box end effector contact. The magnitude of the normal component of the box environment contact forces increases accordingly to contribute to the force balance condition. On the other hand, if we plan to make use of the pick and place strategy to manipulate the box, we have to eliminate the environmental contact constraint from our problem formulation. After solving the modified formulation, the magnitude of the optimal normal contact force for lifting the box of the environment is far greater than the maximum value of the optimal contact force while considering the contact constraints. Upon including the manipulator joint torque constraints in this modified formulation, the problem is deemed as infeasible. To show the flexibility of our formulation, we have also implemented the torque optimization problem, or TOP, which minimizes the maximum torque in a particular joint. The graph in figure 9 shows the variation of the maximum torque on the y-axis with respect to the tilting angle on the x-axis. From the graph, you can see that the maximum torque is lower when we use the TOP as compared to the JFOP. In this paper, we have presented a second-order cone program for computing the grasping force required for manipulating heavy objects with the help of environmental contact. The formulation we have presented is flexible enough to incorporate different objective functions and physical constraints. Given the information regarding the object, the manipulator, and the object contacts, we can compute the optimal values of the contact wrenches and the joint torques. For our future work, we would like to extend the current formulation to incorporate the dynamics of the object as well as the manipulator. In this paper, the path of the object was given as an input to our algorithm while implementing the simulations. However, developing a motion plan to manipulate heavy objects while maintaining contact with the environment is challenging, and it is something we would like to explore further. Finally, we would also like to evaluate our proposed algorithm using experiments. Thank you.